Now next topic, that is electric flux, but electric flux we will discuss later on. First we will discuss the topic next one to it, that is electric dipole. Now what is electric dipole? Electric dipole is a system of two equal but opposite charges separated by some finite distance. Now see here, as shown in this figure, suppose we have a system of two charges equal in magnitude but opposite in polarity. So one charge is plus q, another one is minus q. And these two are separated by some finite distance to a. Then this particular system, that is called electric dipole. Di means two poles, right? One positive, another one negative. Now, with respect to the center of dipole, we consider positive charge and negative charges are at distance a on either side, and this total distance between two charges, that is represented by 2a. Here one very important physical quantity is defined for dipole, and that is electric dipole moment, right? Now electric dipole moment, that is the vector quantity, and that is represented as P equal to Q into 2A. Its unit will be coulomb into meter, and the direction of electric dipole is always represented from negative to positive charge. It implies that it is in the direction from negative charge to positive charge. Clear? Now suppose here we take the magnitude of the charge that is too much large. Means if we take limit q tends to infinity, and if the separation between these two charges that is very small, means limit 2a tends to 0, then in that particular case we can say the electric dipole, that is a point dipole. That is the point dipole. So this one is the concept of electric dipole. Now we have to derive the equations for electric field of electric dipole. Here see, the net charge on electric dipole, that is equal to 0, because net charge, that is the algebraic summation of the charges. So for this system of two charges, both the charges are equal in magnitude but opposite in polarity. So if we take the algebraic summation, then net charge will be 0, but net electric field of electric dipole, that will not be 0, right? So here now we have to discuss the electric field of electric dipole. Clear? Now here we have to find the electric field of electric dipole at any point on the axis of the dipole, as well as at any point on the equatorial line of the dipole or equatorial plane. Say the axis of the dipole, that is the axis passing through both the charges, this one, that is called axis of the dipole, and the equatorial line, that is passing through the center of the dipole and perpendicular to the line joining to these two charges, means here. Okay, so we have to find the electric field on the axis of the dipole as well as on the equatorial line of the dipole. Okay, now see, first electric field at any point on the axis of the dipole. Now suppose, as shown in the figure, we take a dipole. Now axis of the dipole, that is the axis passing through both the charges, or that is coinciding with the line joining to these two charges. Now suppose at point x on the axis of the dipole. We want to find the electric field. Now, this particular point where we want to find the electric field is at a distance r from the dipole. Always remember this thing, the distance of any point with respect to dipole that will be considered from the center of the dipole. From the center of the dipole. So from the center of the dipole, the point under consideration, that is at a distance r. Now at x, if you want to find net electric field, then we have to take the electric field due to plus q charge as well as minus q charge. And then after we have to take the vector summation of these two. Okay. Now, electric field here due to plus q charge, that will be in outward direction. So that will be in the direction as shown in this figure, as well as due to negative charge, that is towards the charge. So E minus q, that will be in the direction as shown in the figure. Okay. Now E plus q, that is equal to, as per equation, kq upon r square. Now the distance of this point with respect to plus q charge. So from center the point is at distance r, center to plus q, that is at a distance a. So plus q to this point x, that is at a distance r minus a whole square we can write, and see the direction of E plus q, that is in the direction of dipole moment. So here multiply this one by p caret, which one is the unit vector in the direction of dipole moment. So this one is now vector form. Then after E minus q, that is equal to, again as per equation, kq upon r square. Kq upon, now distance of point x from minus q, that we can write this r plus a. So here we have to write r plus a square. Now the direction of this electric field, that is in the opposite direction of dipole moment. So here we have to multiply by unit vector but with negative sign, so minus p caret. Now see, here we have to write actually the symbol of vector like this. Okay. Now resultant electric field at point x, that is the vector summation of these two. So resultant electric field vector E, that is E due to plus q and plus E due to minus q. So we can write kq upon r minus a whole square p caret minus kq upon r plus a whole square into p caret. So now we can take kq common and write down p caret outside the bracket. So into bracket 1 upon r minus a whole square minus 1 upon r plus a whole square. So simplify this one and then take LCM. Now see, this into this, r minus a into r plus a, that is r square minus a square and square of it. So that is the denominator. Then numerator, r plus a whole square multiplied by 1 and r minus a whole square, that is with minus 1. So resultantly we will get kq into bracket r square plus 2ar plus a square minus r square plus 2ar minus a square. So r square and a square cancelled. Resultantly we will get E, that is equal to kq into 4ar upon r square minus a square whole square into p caret. But now this 4 is divided in two parts, 2 into 2. So we can write k into 2, then q into 2a into this r p caret as it is, and this one r square minus a square whole square as it is. But q into 2a, that is the magnitude of dipole moment. So we can write electric field E, that is equal to K 2 P R upon R square minus A square whole square into P caret. Now, this one is the equation for electric field at any point on the axis of the dipole. Now, this equation can be used for any point situated at any distance on the axis of the dipole. But suppose here we consider one special case in which we consider if R that is very much greater than A. R that is very much greater than A. Then in that particular case, we can write R square minus A square, that is nearly equal to R square. Now, here we can neglect A square. So we can write now E that is equal to K, this 2P. If A square is neglected, then here we will get R square squared, that is R raised to 4. But in numerator 1 R is there. So 1 R from numerator and denominator will be cancelled. So we can write 2P upon R cube here into P caret as it is. So here we can observe this thing, the electric field of electric dipole, that proportional to 1 upon R cube. And we discussed electric field of a point charge, that proportional to 1 upon R square. Clear to all of you? Then after, electric field at any point on the equatorial plane or line of dipole. So see here, as shown in the figure, consider the equatorial plane, and here the cross section of it is represented, right? So we take this equatorial line, and now we want to find the electric field at any point y, which one is situated at a distance r from the center of the dipole. So concept is simple. We have to take electric field at y due to positive charge as well as due to negative charge, and then after we can find the resultant one by taking the vector summation of these two fields. Clear? Okay. Now see here, from the center of the dipole plus charge that is at a distance a, and negative charge that -1 that is also at distance a. Then center to y, that is r. So from each charge, this particular point that will be at a distance under root r square plus a square as per Pythagoras theorem. Clear? Now, E due to plus q charge. So magnitude wise we can write k q upon distance square, so under root r square plus a square whole square, so that is simply k q upon r square plus a square. And due to negative one, so E minus q, that is equal to k q upon r square plus a square. Same way. But see here, the direction of E plus q, that is outward here, means that is in the direction plus q to y direction. But due to negative charge, that is towards the charge, so that is from y to minus q. So E plus q and E minus q will be in the directions as shown in the figure. Now, if we consider here the angle theta as shown in the figure, then if we take the components of these electric fields in horizontal and vertical direction, then we will get for E plus Q the component E plus Q sine theta in positive y direction, means vertically upward, and in positive x direction we will get E plus Q cos theta component. Similarly, for E minus Q, the components, so in positive x direction here we will get E minus Q cos theta, and in negative y, means vertically downward, that will be E minus Q sine theta. But see here, magnitude wise E plus Q, this one, and E minus Q, both are same one. It implies that E plus Q sine theta and E minus Q sine theta, which are equal in magnitude, opposite in direction, will cancel each other. It implies that here, see, when E plus Q cos theta and E minus Q cos theta both are in the same direction, then the resultant electric field, that will be the summation of this one. So we can write now net electric field at y, that is E plus Q cos theta plus E minus Q cos theta. But now see, the dipole moment, that is from negative charge to positive charge, so the direction of the dipole moment, that is this one. And now see here, at y, the net electric field, that is in the opposite direction of dipole moment. So we can write now net electric field E, that is E plus Q cos theta plus E minus Q cos theta. Now we have to multiply here by minus P caret. Now E plus Q cos theta and E minus Q cos theta are equal in magnitude. So we can write 2 times KQ upon R square plus A square cos theta. But from figure we can write cos theta, that is adjacent upon hypotenuse. So A upon R square plus A square raised to 1 by 2. So here see, we can write minus 2KQ upon R square plus A square cos theta is replaced by A upon R square plus A square whole raised to 1 by 2 into P caret. Now, resultantly we can write therefore E equal to minus 2KQ into A upon this R square plus A square whole raised to 1 and this R square plus A square whole raised to 1 by 2. Resultantly will give you R square plus A square raised to 3 by 2 into P caret. So now this one is the equation of resultant electric field at point Y, which one is situated at distance R from the center of the dipole on the equatorial line. But this Q into 2A, that we can replace by dipole moment also. So in terms of dipole moment, our equation will be minus K P upon R square plus A square raised to 3 by 2 into P caret. Clear? So this one is the equation for electric field at any point situated at any distance on the equatorial line of the dipole. But again here we can consider one special case in which if we take R is very much greater than A, then again we can neglect A square. So we can write R square plus A square, that is nearly equal to R square. So here in this equation, if A square is neglected, then R square raised to 3 by 2 will give you R cube. So we can write E equal to minus KP upon R cube into P caret. So E proportional to 1 upon R cube. Okay. Now see here the equations. E, that is equal to minus Kp upon R cube into P caret. And here E, that is K 2P upon R cube into P caret. It implies that If we consider 2 points, one on axis of the dipole, another one on the equatorial line of the dipole, at the same distance r, then from these equations we can say this thing: the electric field on the axis of the dipole, that will be twice than the electric field at any point on the equator of the dipole, for the points which are situated at the same distance. Clear to all of you? Then after the topic, that is physical significance of dipoles. Now see, we can observe some molecules for which the centers of positive and negative charges are at the same place, or we can say coinciding each other. See here, CO2. So the structure of CO2 is such that the centers of positive and negative charges coincide. These type of molecules are called non-polar molecules. So they does not possess permanent electric dipole moment. But no doubt, in the presence of electric field, the dipole moment is induced in it. But some molecules are such that for which the centers of positive and negative charges are separated by some finite distance. It implies that such molecules possess permanent dipole moment, whether the electric field is present or not. So, see here, the example is given to you, H2O. So for that also, the centers of positive and negative charges are separated by some finite distance. So we can say it possesses permanent dipole moment. Such molecules are called polar molecules. And now here we can observe very interesting behavior, very interesting phenomena in the presence and absence of electric field related to these molecules. So when these molecules are in the electric field, then the behavior, that is interesting one. So all these things we have to study, and therefore this concept of dipole moment and its electric field, that is very important thing. Clear to all of you? Then after illustration number 1.10, two charges plus or minus 10 microcoulomb are placed 5 millimeter apart. Determine the electric field at a point P on the axis of the dipole 15 centimeter away from its center O, on the side of the positive charge as shown in the figure A, and B, a point Q 15 centimeter away from O on a line passing through O and normal to the axis of the dipole as shown in figure B. Okay. Now see here, see the figure in text, but here the calculations carried out in text are lengthy one, so you have to follow it. Say, suppose first we think about the given data. So magnitude of the charge, that is 10 microcoulomb, so that is 10 into 10 raised to minus 6 coulomb. Now R, that is 15 centimeter, so 15 into 10 raised to minus 2 meter. Then A, say the dipole, that is with length we can say 5 millimeter. It implies that from center each charge is at 2.5 millimeter. So A, that is 2.5 millimeter, so that is 2.5 into 10 raised to minus 3 meter. So we can write that is 0.25 into 10 raised to minus 2 meter. Now On the axis of the dipole, we can write the equation of electric field, that is K Q 4 A R upon R square minus A square whole square. This we already discussed in the previous theory. So now direct substitute the values. K, that is 9 into 10 raised to 9. Q, that is 10 raised to minus 5, this one. Then 4A, that is 0.25 into 10 raised to minus 2. R, that is 15 into 10 raised to minus 2 divided by this R square. So 15 into 10 raised to minus 2 whole square and minus 0.25 into 10 raised to minus 2 whole square and square of entire this one. Then solve, you will get the answer. Clear? Then if we consider here A, that is very much less than R, then simply you can use the equation K4QA upon RQ. Again here substitute the values of K, Q, A and RQ and solve this one. You will get these two answers nearly equal. Similarly, on the equatorial line, we can use the equation E equator, that is K2QA upon R square plus A square raised to 3 by 2. Now substitute the values of K, Q, A, R and A here and then solve it. Then after, by considering A very much less than R, we can use this equation K to QA upon R cube, and again if we substitute the values of K, Q, A and R and then solve it, you will get the answer. And now we can compare these two, will be nearly equal. It implies that by calculation here it is represented if R is very much greater than A, in that particular case we can use this particular equation directly. So that is just represented here. Okay, but see, in text this one is calculated like that, first due to positive charge, then due to negative charge, and then after taking the summation, the resultant field. But in theory directly we derived this equation, and this equation is valid for this one and this one. That is valid for any point situated at any distance. Clear? So directly we can use it. And these two equations, this one and this one, are special cases. And here compared to this 15 centimeter, 2.5 millimeter, that is very, very small. So we can neglect it, and then it is represented here by calculations. Yes, we can use in this type of cases this special case equation also. And then we can check this thing. If we take the ratio of E axis upon E equator, then it will come to 2. Because here the point is at the same distance on axis as well as on equator. Clear? Now we have to understand the behavior of the dipole in uniform external electric field as well as in non-uniform external electric field. So what happens when the dipole is placed in uniform electric field? Okay, now see here, suppose as shown in the figure, we have uniform electric field, that is in the direction as shown in the figure. Uniform electric field means the intensity of electric field at each and every point, that is same one, and at each and every point the electric field that is in the same direction. So when we represent the uniform electric field, at that time we represent it with equispaced parallel arrows. So at present the electric field that is in the direction as shown in the figure, and that is the uniform electric field. Now suppose the dipole is placed in the uniform electric field at angle theta with respect to field. Angle theta, that is considered between dipole moment and electric field. Okay. Now we already studied this thing. When any charge is in the electric field, the force acts on it, that is Q into E. So here on the positive charge, the force that will be in the direction of the field, and on negative charge it is in the opposite direction. So see here, the force on plus Q charge, that is in the direction of the field, and that is QE. Then force on the negative charge, means on minus Q, that is in the opposite direction of the electric field, that is minus QE. But now see here, two forces are acting. These two forces are equal in magnitude and opposite in direction. So net force will be zero, but these two forces are not collinear. It implies that it will form a couple. And now it will produce the torque. Clear? So here, due to net force that is zero, there will not be the translational motion of the dipole. But due to torque, we'll get the rotational motion. So now, here, the torque, that is how much? See here, the distance between these two charges, that is represented as 2a. Now this angle is theta, so this one is also theta. So perpendicular distance between these two forces, that is given by 2a sine theta. Now as per definition of the torque, we can write magnitude of any one force into perpendicular distance between two forces, that is the torque. So magnitude of the force, that is QE, and the perpendicular distance between these two forces, that is 2a sine theta, as shown in the figure. So QE into 2a sine theta. So tau, that is Q into 2a. So torque tau, that is force QE into 2a sine theta. So we can write that is tau equal to Q into 2a into e sine theta. So tau, that is Pe sine theta. So in vector form, we can write torque tau, that is P cross E. Okay. Now under the effect of this particular torque, the dipole will be rotated in such a way that theta will be decreasing 1. And when it is aligned with the field, then theta will be 0, so torque will be 0. Clear? So whenever the electric dipole is placed in the external uniform electric field, the torque acts on it, and under the effect of it, it will try to align itself in the direction of the field. Now, if the electric field is non-uniform one, then the force on positive and negative charge will be no doubt opposite in direction, but not equal in magnitude, because field is non-uniform. Means at a different position, the field intensity is different one. So at the position of positive and negative charge, the field intensity, that is different one. So forces are different in magnitude, but opposite in direction. So here some net force will be there, as well as some net torque will be there. And under the effect of this net force and torque, okay, it will execute the translational as well as rotational motion. And rotational motion will be executed till it is aligned with the field. And once it is aligned with the field, then after the translational motion will continue. Clear? So this one is the behavior of dipole in external field.